Alrighty, welcome. So today we're going to be having a look at a quadratic trigonometric equation. So there's one bit of notation I want to go through. If we ever write, say, sine squared x, something that looks like that, that actually means, in terms of standard notation, would mean sine of x squared. Okay, but for notational purposes, it becomes often quite useful to shorten these things, and so we remove the extra brackets and we put the squared next to the sine. So that actually is, so if you ever see something like that, you know that that is now a alternative way of writing it. Alrighty, so this equation here, we're solving for x, and between 0 and 2 pi, so we're thinking in radians, and you can see here that it does not look solvable in its current form. We have two sine functions, one here and one here, opposite sides of the equation, and it doesn't look like it's at all solvable. So let's try and solve it. Now, like in previous ones where we've been looking at it, the key here is actually the fact that it's a quadratic. And it's a quadratic in disguise. So let's undisguise the quadratic. So let's just say sine of x, let's call that k. Well, that means sine squared of x, well, since that's just sine x squared, would be k squared. Alrighty, so now we've got our substitution to be used. So let's substitute into the equation. So we get 1 minus 2 sine squared x, well, that's k squared, equals sine x, which is just k. So we've just got a quadratic. Now, whenever I'm looking at a quadratic, the first thing that I'm looking at is the k squared term, the x squared term. Why? Because A, I don't want it to be negative. It's going to make my life easier if it's positive. And B, I'd like it to not have I would like it to have a 1 at the front. Unfortunately, it has a 2 at the front, so it's not a monic equation. But anyway, we can rearrange the equation, add 2k squared to both sides, take 1 from both sides, and now we have a quadratic. And now we need to factorize it. I'm going to use the t-chart to do this. So we're looking for something that multiplies 2 times negative 1 is negative 2, and adds to 1, b. Alrighty. Well, it's going to have to be 2 times negative 1. That's going to be the only one that's going to work. And so we're going to use decomposition to then factorize this. So split the middle term into plus 2k minus 1k minus 1. Pull out the factor of 2k, and we're left with k plus 1. And pull out the factor of negative 1, and we're left with k plus 1. Pull out the pair, and we have now factorized the quadratic. Alrighty, but again, that doesn't actually tell us the solutions. In order to find the solutions for k, well, we need to use null factor law. The first solution is just going to be that k1 is equal to negative 1. The second solution is a little bit harder to work out, but we're going to get 2k2 minus 1 equals 0. So k2 has to be equal to a half. Just skipping a bit of algebra there. But remember, at the beginning, we substituted sine of x as k. So we need to now unsubstitute. So let's write sine of x equals negative 1. Alrighty, so sine of x equals negative 1. There's only a couple of solutions. And how can we find the solutions? Well, for negative 1, it's not actually on any of our unit circles. Oh, sorry, and our triangles. It's only going to appear on the unit circle. So let's look at the unit circle. So on the unit circle, where is sine going to be equal to negative 1? Well, sine is to do with the y-axis. And the y-axis is only negative at this region down here, and it's only going to be negative 1 at that particular spot, which is an angle of, well, 3 pi on 2, or 270 degrees. So we've got only one solution, and it's 270 degrees. So x must be equal to 3 pi on 2. But as with all of these things, these have general solutions. So just for completeness, I'm just going to put plus 2 pi n for n some integer. Alrighty, let's now repeat this, but for when it equals a half. I still haven't figured out any of the solutions just yet, but we'll be getting there very soon. So this gives us sine of x equals a half. Now this does appear in a triangle, so let's draw up our triangle. is going to be the 1, 2, root 3 triangle, hence it's got 1 and 2 in it. And we've got the two angles here, pi on 6 and pi on 3. Alrighty, so we want this to be the opposite, this to be the hypotenuse, well this has to be the angle, so we get x is equal to pi on 6 plus 2 pi n for some n in integers. Or let's make it 2 pi m for m in integers. Alrighty, but remember that's only one solution, because remember, because of symmetry, we're actually going to have multiple solutions. So let's draw up a unit circle. Okay, so pi on 6 here, and we're looking for the sine quadrant, because that's the all quadrant. Yep, so that's going to be the other place where it's going to be. And this angle here, well, that's going to be, that angle there is going to be equal to 5 pi on 6. Okay, so, or x is equal to 5 pi on 6 plus 2 pi k for, oh, I can't use k, I've already used k, 2 pi j for j, which is some integer. Alrighty, so I've now got 3 families, and we've got to look to see whether any of their the next ones are actually going to be solutions. However, we're quite lucky here. We're only looking for one rotation. So when we're in one rotation, when you add 2 pi, that's going to take you outside of that one rotation, because that's going to get you bigger than that. The only exception to that would be 0, because if you add 2 pi to 0, that's also going to be a solution. So in this case, I don't have to worry about any of the 2 pi n's or m's or j's, but that is only because of the domain I've been given. If I had a bigger domain, I'm going to have lots more solutions. So x is equal to 3 pi on 2, or x is equal to pi on 6, or x is equal to 5 pi on 6. And those are my 3 solutions that are within this region. Alrighty, so there's the challenge. I'll see you in the next one. Goodbye.